Here we're going to solve a kinematics problem, and the one we're going to pick is problem 48 in the textbook. Here we have a bizarre situation of a hoodlum who is throwing a stone downward with a speed of 12 meters per second, and we're told that it does this from a building that's 30 meters high. So although we're only given two numbers, we're actually given more information than that. So we need to figure out how to break this down into, again, our table of kinematic variables. This particular motion only has 2 points, namely at the start, when the stone is at the top of the building, so it's a height of 30 meters, and we're told it is thrown downward, right here, downward, with a speed of 12 meters per second, so its speed is 12 meters per second. Since this is the start, we'll define that at time t equal to 0. And the only other point we're worried about is when it hits the ground, so we'll call that the end, and we don't know that time. We do know where that is, it's on the ground, so that's 0. We don't know how fast it's going, so we'll put a question mark there. This is free fall, so we do know the acceleration. It's given implicitly because we're in free fall. The acceleration throughout the entire motion from when it's released to when it, just as it hits the ground, is minus 9.8 meters per second squared. Now, what we need to do is look at what it is we're asked to find. Well, what we're asked to find in part A is basically how long it takes to reach the ground. So that's the unknown time t here. And in part B, we're asked to find its speed as it hits the ground, and that is this unknown velocity right here, which is its final velocity. Now that we have what we know and what it is we want to find out, next thing we need to do is figure out how do we do that. Well, what we're going to do is take a look at our kinematics equations, which are right here. And in this we know acceleration, initial velocity, initial and final position, and we want to find a time. And the question is, which one of these equations has that? Well, looks like equation number 1 right here does. So let's take this one and copy it. And go back to where we were. Right here, and let's paste it. Here's our equation. Now, we know the acceleration, because we're in free fall, minus 9.8 meters per second squared. We know our initial velocity, minus 12 meters per second. And we know where we start out, that's our 30 meters. We know where we end up on the ground, and that's 0. And the thing we don't know is the time, and that's the only unknown in the equation. So we can write this down, and we have an equation that says 0 equals 30 minus 12t plus 1/2 at squared, which is minus 4.9 t squared. Now what we have is a quadratic equation to solve, with our unknown being t. Now we could sit down and write down the quadratic equation and plug all the numbers in. However, we're lazy, so we're not going to do that. Instead, we're going to get our calculator out. And on our calculator, we should have on there somewhere this program right here. This is a program TI has written that solves quadratic equations. That is under the App button on your calculator. Select that, and the option we want to do is solve a polynomial. Select that, and then it'll eventually prompt you for entering the coefficients, so we enter them in. This right here is the 1/2 g, minus 4.9. This right here is the minus 12 meters per second, the initial velocity. And this right here is the height of 30 meters. Then we click the solve button right here, and we get our 2 answers. And since it's a quadratic, we always get 2 answers. And the question is, why 2 and what do they mean? So, way to do that is to draw a graph. And here we have a graph of basically this curve right here is basically y equals 30 minus 12t minus 4.9 t squared. Graph is a function of t. And here we can see our two solutions. They're right here and right here. This right here is the minus 3.985, etc. And this one right here is the plus 1.536, etc. This right here is where the stone starts out. This right here, this slope is the minus 12 meters per second. This is time forward, so obviously the stone is going to land after it is dropped. This right here is our solution. However, if we just draw the equation as a parabolic curve, the curve does in fact cross the axis at 2 points. This right here is a perfectly valid mathematical solution to the problem, but it's not physically reasonable because before the stone was thrown, presumably right here, our hoodlum was just holding on to the stone. And this is the actual position before it was thrown. It was not a parabolic curve, it was a flat line. Presumably, he was just holding it. So therefore, this part of the curve does not represent the problem. The problem really is the stone being held stationary and then being thrown down and hitting the ground and then presumably being stationary again. So the solution is just this 1.536. Now we have to be careful because we have to watch out for our infamous sig figs. How many digits should we be citing? Well, let's go back and look at the problem and notice we are given 3 sig figs in the data we are given, 30.0 meters and 12.0 meters per second. G right here, we have to be a little careful about. We always just write down 9.8. But at Wellesley, Massachusetts, at about 42 degrees north, G is actually more appropriately, 9.80350 meters per second squared. And our 9.8 is valid to 3 sig figs. Our data is to 3 sig figs, so therefore our answer should be given to 3 sig figs. So therefore we should round that off and say the answer is t is 1.54 seconds. That would be the correct answer. Now we want to do part B. Part B, we're asked to find the velocity when it hits the ground. Now again we need to go look at our kinematic equations down here. We want to find a velocity and therefore we need to use equations 2, 3, or 4 because they're the only ones that have the final velocity. Equation 2 is the simplest, so that's therefore the one we probably want to use. So let's go back and paste that in. This is our equation. This right here is our final velocity. This is our initial velocity, which we know was the 12 meters per second downward. The acceleration is, again, our minus 9.8 meters per second squared. And the t is the time it took it to fall, which we just found. That's the 1.54 seconds. So all we have to do is plug them in, and we get the velocity that it hits the ground. Again, citing to 3 sig figs, is minus 27.1 meters per second. And that's the speed it hits the ground at. The minus sign means it's going down. And this right here is the rate. So it's the magnitude and direction. So the negative sign tells you that the stone is, surprisingly enough, falling downward. And we are done.